Okay, so this week you guys have been working with systems of equations, and the textbook just briefly talks about non-square systems. And so I wanted to go a little bit more detail into this, just so you would have sort of an idea of what it means to be square versus non-square, how you write the solutions, because the how you write the solutions is kind of confusing. So I just wanted to kind of go into that. So first off, we will start with what is a system. So a system is just where you have two or more equations that are considered together, and the solution needs to work in all of the equations. So if we have two variables with two equations, then our solution is an ordered pair x and y. And we indicate that we have a system by using these little curly braces. That's the notation for systems. Sometimes you'll hear these called simultaneous systems or simultaneous equations. That's actually calling it simultaneous equations is used more in engineering versus mathematics, where we'll call it a system. So it's important to kind of know the difference because you'll see other terminology used. So square versus non-square. So systems are square if they have the same number of equations as variables. So if you have two variables, it requires two equations. And we actually get the name of this from matrices. So next week, we're actually going to be looking into matrices, which is like the basics of linear algebra. And, oops, didn't even notice I switched slides. And square systems, when you turn it into a matrix, are basically the coefficients are square. So an example here of a square system. I'm just going to make up numbers. When we have this in matrix form, we usually just take the coefficients and we kind of write our system like this. So this will make more sense next week. But you can see that the coefficients in front of the x and y, it's a square. So that's why it's called a square system. And square systems have, you know, we know that there are solutions to these types of systems. Sometimes there's no solution, sometimes there's infinite many, but most of the time there's solutions. Non-square systems either have more equations than unknowns, so you might have two variables and three equations, or you have more unknowns than equations, so maybe you have three variables and two unknowns, and these will look like a rectangular, thus non-square. So an example would be if we had 2x plus 5y minus 10z equals 1, and then 3x minus 7y plus z equals 5. This is a non-square system because if I put it in its matrix form, which again will make sense next week, but if you just look at the coefficients, it's not a square, it's a rectangle. And then this is also a rectangle when we write our variables. So we don't get squares here. So this is why it's called a non-square system. It's because you don't have the same number of dimensions. Your input and the output, they don't match, essentially. So the way we solve these it's a little trickier, mostly in how you write your solution. So I've actually made a table here. So if you have the same number of equations as you have variables, so two equations, two variables, you can either have no solution, one solution, infinite solutions, but we know that we can solve this. If you have fewer equations than variables, so if you have two equations, three variables, like the non-square system that I showed here at the bottom, then you have infinite solutions because you don't have enough information. So in order to at least have the possibility of one solution, you need to have at least as number of equations as variables. So if you don't have enough information, there's infinite solutions. If you have more equations than variables, you can still have no solution, one solution, infinite solutions, because sometimes the extra equations are unnecessary. So if they're unnecessary and they're just repeats of your other equations, then you can still have one solution. But sometimes those extra equations can give you contradictions, so you could have no solution. So you have to kind of, the most important thing here to note is this in the middle, because in real life, if you have to do anything with systems of equations and you are coming up with your own mathematical models, if you want to make sure you have at least the same number of equations as variables, because if you don't, you have infinite solutions. So, if you know that you have 3 unknowns, make sure that you also have written down 3 equations. And this is also helpful for, the assignment this week. If you know you have 2 unknowns, you better have written down 2 equations, because if you don't, then you don't have enough information. So when you have systems that are not square, we need to use Gaussian elimination. You could do this graphing, but if you have 3 variables, you can't really graph. You could do substitution, but it can get confusing. So the best way is by Gaussian elimination. So you're basically going to put the Gaussian elimination in row echelon form, and that helps you determine whether there are infinite solutions, no solutions, like you can visually see when you do this, when it's in row echelon form. And then once you've got it in that form, you're looking, are there contradictions? If so, there's no solution. Are you looking, did you actually get a solution for a variable? Okay, then there's a single solution. Otherwise, you might have infinite solutions, and there's infinite solutions. You have to follow these 4 steps. So whatever your bottom equation is, usually you'll see these with x, y, z equations. You'll let z equal a. You just pick a new variable. And then you're going to plug that in, replace your variable z with a, and solve for y. And then you're going to have y in terms of a and z in terms of a. And you plug those in for x, solve for x, and then everything's going to be in terms of a. So you have 1 unknown, and that's how you write your solution, and you're going to write it as an ordered pair. So this makes way more sense if you see me do it, if you see it actually worked out. So I only have 2 equations or 2 examples because these things do take time. And I know that most people don't like Gaussian elimination, so it takes a while. I am going to be doing this very organized. So I'm going to show you how I organize my Gaussian elimination. So hopefully you can then also do this when you're doing your own examples of this. So this is not square. This is non-square because we have 3 variables but only 2 equations. So we're likely to have infinite solutions. We're not guaranteed to have infinite solutions, but most of the time it does result in infinite. Wait a minute. Yes, we are guaranteed to have infinite solutions. What am I talking about? The other way around, that you're not guaranteed. We are guaranteed to have infinite solutions here because we don't have enough information. So it's just a matter of how do we write these solutions. So Gaussian elimination, you need to have it in a stair step. So if I'm going to have something with x, y, and z, then the next one has to have y and z. So if we had 3 equations, then the next one would be z, but we don't. We have only 2. So I need to get rid of x in that second equation. So that way we're putting it in Gaussian elimination form, in row echelon form is what we call it. So I do this with elimination. So I'm going to use elimination to get rid of the 5x. And I'm going to do this by taking the first equation, multiply it by -5. We're going to add, and that will give us our new equation that we can replace the second row with. So here's how I organize everything. First off, I label my equations. And then I actually write down what I am doing. So I am going to eliminate x in equation 2. That's my goal. So I just write this down. And so I'm going to try to color code this as much as possible. If you want, you can even put equation 2, put that in a different color just to kind of help it be, offset. But I'm taking that first equation and I'm going to be multiplying it by -5 because I need to get it to cancel out with the 5x. So notice how I'm showing my work here. Oops, like that. So I'm putting the original equation in white, and then what I'm doing in a different color in this green. And then I'm not even bringing in equation 2 yet into this. I am just going to distribute. So this gives me -5x plus 15y minus 10z equals, and then I did this earlier, this gave me -90. So then what I do is I leave myself a gap and I rewrite this equation. And now I take equation 2 and write it underneath it. And then I add them together. So my x's are going to cancel out. I'm going to get 15 minus 13, so that's 2y. -10 plus 12 is going to be plus 2, so it's going to be plus 2z. And then we're going to -10. So that now gives us our new equation. And before I go to the next step, I rewrite my system. So that way I know what my system looks like. So I just rewrite the whole thing. And if we look at our numbers, we've now got an equation 1, and then this is now number 3. So we've replaced the second equation with the third equation because we got rid of that x. Now, row echelon form requires that in that second row, you have a 1 in front of the y. You don't have a y, so I need to take that second equation and I need to divide it by 2 or multiply by 1/2. And I usually write mine as multiplying by 1/2 because that's what we do when we do stuff with matrices, which is, you're going to be doing in a few days. So we're taking you along the route to there. So I'm going to again write down what I'm doing. So I just write down get y, not 2y in 3. So I need to multiply by 1/2. So I've got 1/2, and then that was 2y plus 2z. And then I have to also multiply the other side. And the nice thing about color coding like this is that you can see very clearly you are making sure you're doing both sides, because that is something that a lot of people forget, is that they will do one side but not the other side. So by color coding the way that I have here, you're making sure that you can visually see, okay, I did do it on both sides. So I'm going to distribute 1/2 times 2 is just 1. So I have y plus z equals -5. And so now we're going to call this equation 4. And I'm going to rewrite my system again. So we have x minus 3y plus 2z equals 18. And now we're replacing 3 with 4. So now we have y plus z equals negative 5. So this is row echelon form. This is as far as we can get because we don't have a third row. So we are now in row echelon form. And this is where you start doing back substitution. But when you don't really have like a third equation for z, so we know we're going to have infinite solutions. We're guaranteed here. So we're going to have to do some back substitution. But our first step is to let z equals a. So this is going to be, now we're going to be starting to do the back substitution. So I start with saying let z equal a. So let me number these. We had equation 1. This is equation 4. So then equation 4, instead of z, it's now y plus a equals negative 5. And so when you solve, you get y equals negative 5 minus a. So you just subtract a from both sides. Now I'm going to take equation 1 and do my back substitution. So we've got x minus 3y, but instead of y, it's negative 5 minus a. Then plus 2z, but instead of z, it's a. And then equals 18. And now I'm going to solve for x, and I'm going to have a's in my answer. That's perfectly fine. That's what we're looking for here because there's infinite solutions, and you just basically get a solution by picking a number for a. So I'm going to start by distributing here. I get plus 15 plus 3a plus 2a equals 18. X plus 15 plus 5a equals 18. I'm going to subtract 15 from both sides and subtract 5a from both sides. 18 minus 15 is 3. And then I subtract 5a. So I probably should write that down. Minus 15 minus 5a minus 5a. So now I've got z, y, and x all in terms of this new variable a. And this is just saying we've got infinite solutions. You pick a number for a, you plug it in, and this is how you get your x, y, and z. So instead of having to resolve this thing every single time to find a solution, we've got it in terms of some variable that you can plug in. Now, when we write our answer, it's going to be an ordered pair. You start with your x, which is 3 minus 5a, then your y, which is negative 5 minus a, and then your z, which we called a. So there are infinite solutions, but this describes how you find your x, y, and z based off of those numbers. And you pick a number for your z, and then you plug it in, and you can get the other ones. The way that we're writing these things with the variable a, this is actually very common in linear algebra. Now, I don't think anybody here is required to take a linear algebra class, but if you do, I don't know, for whatever you want to go in an advanced computer science or go beyond a bachelor's, you'll probably end up having to take a linear algebra class, engineering, computer science, something like that. And you will actually have to do things like this. So it's sort of leading you into a whole area of math that is advanced math that you need if you decide to get like a master's degree. Some computer programming degrees and engineering degrees require a linear algebra class at the undergraduate level. Ours don't. So you just get a little taste of it in this class, but you don't have to take a whole entire class on it. But it's kind of, we're giving you a little taste for something that, you know, if you do decide to go on. So are there any questions on this example and how I came, you know, maybe how I organized it or how I knew what step to do when, or, you know, how we got our answers? Are there any questions? Okay. I wanted to give you guys enough time to think through this. So this is the most common form of non-square equation that you'll see. It would be something like this, where you just don't have enough information and you try to come up with a solution, but it depends on what your input is. The other kind is this way, where you have more equations than variables. And so this, you may have one solution because your third equation could be an extra. You may have no solution because two equations may give you contradictory results, or you may have infinite solutions. So it's kind of like, well, how do you solve this? We're still going to do Gaussian elimination. And it's going to be x, and then your y, and then we were going to have just y, and then we're going to end up with basically an extra y when you try to do this in Gaussian elimination, because you could try to get rid of that third variable and just get 0 in the bottom row, but I like to get y in both the second row and the third row, just so I can easily see if there's a contradiction. Because if it's a contradiction, you'll have two different values for y. If you get the same value for y, then it's not. So I like to get it in that form, but otherwise you could try to get it where you've got zeros and your goal is to have it equal to 0 there when you try to get the Gaussian elimination. But the most important thing is you're just trying to see if you're getting a contradiction as you solve this. So I'm once again going to number my equations. 1, 2, 3. And I'm going to get rid of x in equation 2 and equation 3. So I'm going to try to do both of those at the same time. And so I'm going to do this sort of side by side. So we're going to eliminate x in 2 and 3. So to get rid of x in equation 2, I'm going to take my first equation and multiply it by -4. So I've got -4 times x plus 2y equal, and then I have to remember to do it on the right, -4 times 3. And I'm not going to kind of do both of these like side. I mean, I'm going to put them side by side, but I'm going to just finish one first and then do the next one on the right side. So I'm going to distribute. I got -4x minus 8y equals -12. And I'm going to take that equation and I'm going to combine it with equation 2. So my x's cancel. I have -8 minus 15 is -13. Y, -12 plus 6 is -6. And so this is going to give me an equation 4. Now to eliminate the x in equation 3, I need to take the first equation and multiply by 7. So I have 7, and then I'm going to multiply by 7. I multiply 7 by x plus 2y, and then 7 times 3. So that gives me 7x plus 14y equals 21. And now I'm going to add that to equation 3. So it's negative 7x plus 8y equals 9. The x's cancel. 14 plus 8 is 22. 21 plus 9 is 30. And then this is equation 5. So I'm going to rewrite what I have, and I'm going to replace equation 2 and equation 3 with equation 4 and equation 5. So our system that we have so far, we have x plus 2y equals 3, negative 13y equals 6, and 22y equals 30. And this was equation 1, 4, and 5. So we need to get rid of the coefficient in front of the y. If you're looking at this, it looks like we're going to get a contradiction, but it's a lot easier to see that when you get rid of the coefficient in front of y. So we're going to actually solve these for solve equation 4 for y, solve equation 5 for y. And technically, you know, this is part of the Gaussian elimination, is we want to get that down to just whatever that variable is. So we're going to solve for y in 4 and 5. So we have equation 4, which is negative 13y equals 6. So if you just divide both sides by negative 13, we're going to leave it in fraction form. Y equals negative 6 over 13. And then the other one, we have 22y equals 30. You divide both sides by 22. So we got y equals 30 over 22, which I'm going to reduce. I'm going to divide those both by 2 because they're both even. And that gives me 15 over 11. So we have two different values for y, and they are not the same y. So if we put this back in our form, we have x plus 2y equals 3. We have y equals negative 6 over 13, and y equals 15 over 11. We have a problem. If you get a contradiction there, we have two different values for y. This tells us that this system doesn't have a solution because we can't get the same value for y. We have a contradiction here. And so we have no solution in this case. And this one we can graph. I didn't graph the other one because it was x, y, z, and graphing stuff with 3 variables, well, it's very hard to visualize. But here we've got 2 variables, so I can graph the original system, and so you can see what this looks like. So I'm going to just pull up Desmos. And I'm going to type in our original 3 equations. So x plus 2y equals 3, or x minus 5y equals 6. You can see those two intersect, but when I put in the third one, it doesn't intersect at the same place. It intersects in a completely different location. So a solution would have all three of these in the same place, but they're not. So this answer works for two of these. This one works for two of these, but we don't have an answer that works for three of these. So we have an extra equation, but we can't find a single number that works in all three. So there's no solution. Sometimes there is. Sometimes, it will go through all three and you have a solution. Sometimes one of these equations will be overlapping the other one, and then that's where you get infinite solutions. Or it could actually, you end up with one solution wherever it's overlapping. It depends on how much overlap there is. So I was like, I don't know how I can make this kind of. I was thinking like, oh, I can maybe make these overlap and mess around with the numbers, but I don't know how that's gonna. I can't visually do that. But let's say the green and the blue line were the same equation. Actually, I could do that by just doubling this. So if your green and blue were on top of each other, you would have one solution because there's still only one intersection point here. If all three equations are on top of each other, so if this was negative 21 plus 24 plus 27, if all three of them are on top of each other, then you have infinite solutions. In our case, we had no solution because we didn't have overlap between, we didn't have a single location where all three intersected. But those are the other possibilities when you have a situation like this, is that they're all the same equation, or two of them are the same equation and the third is different, or if all three are different and they're not going to necessarily overlap most of the time. And the only way that you really figure that out is either you can graph it if it's an x and y, or you can solve it and you're looking for contradictions. And if we got the same value for y, then we'd be good. We know, okay, these two of the equations are the same, so we're going to have a solution.